All right, so, as promised, we're gonna talk, I call this section like more on integrality. But basically, we're gonna look at some properties that integrality enjoys, and they're actually of great importance by themselves. So let me give you this, theorem that we were talking about last time. Uh, 5.1. Let R and T be rings and U an element of ring containing T. And U an element of a ring containing. If U is integral over this T and T itself is integral over R, then U is integral over R. And this is transitivity of integrality. So, and actually it's funny because when I visited Philadelphia last week, somebody asked me this question, and asked if you have, so the question that was phrased to me is, suppose you have a collection of algebraic energies. So these are all things that are integral over Z. And you look at a polynomial, a monopolynomial whose coefficients are all these algebraic energies. Is that also an algebraic energy? This theorem says yes, right? Because this theorem says that U is integral over what extension I get when I join those elements to roots. And of course, that extension, since they're all integral, is integral over R, then U must be integral over R as well. So, suppose U is a root of xn plus tn minus 1, xn minus 1, plus t1x plus t0. So we know that U is the root of this. Now, here's the easy observation. Let M now just take R and stick in all the coefficients and the U itself, which is integral over those coefficients. Because really, you don't need U to be integral over all of T, right? You only need it to be integral over the smallest ring that contains those coefficients, right? M is finite generated. R mod. And U is and so that will be useful transitivity of integrality. Okay, any questions on that? Now what I'm going to do is I'm going to launch into this. We now consider some properties that an extension rings may have. And of course, implicitly with that, I mean may or may not have. You've heard me use at least some of this terminology before. We say the extension R inside T is line over There are entirely too many abbreviations in community biology. I guess I've got to keep up with the edition. The extension's lying over if any prime in R is contracted from a prime in T. Any polynomial, there exists some any prime ideal down in R, there's a prime ideal upstairs that contracts to it. Sometimes we say that Q lies over P. Notice this only, well, maybe I should just get this all down. Some examples then. We say that R inside T is going up. If given a chain of primes of R, primes, and a prime ideal that contracts to the small one, then there exists Q1 in T prime such that it is contained or contains Q0 and contracts to P1. Let's say Q1 such that Q0 is contained in Q1 and Q1 intercept R. I like to draw a diagram with going up and going down. So at the R level, this is going up. So here's your diagram. You've got some primes here, and you also happen to have a prime here at the T level. Q0, and Q0 contracts to P0. So the intercept is down to R with this. Then you can go up to a prime Q1. It contracts to P1. This is, so you see, having the ladder below allows you to climb up above. That's what going up is. I bet you can probably guess what going down is. Well, let me get you a little bit more before you guess that. R inside T is going down. Well, you just go down instead of up. If given primes, I really don't like that there. That's and a prime that lies over the bigger one. Then there exists a prime Q0 such that Q0 is contained in Q1 and Q0 intersect R. And so here's kind of a diagram of that situation. At the R level, again, you've got to change 2 primes. But this time, you know that there's something lying over the big one. Going down allows you to climb down instead of up. So you can build Q0, whose intersection down here is Q0. And finally, we say the extension's incomparable extension. If given primes Q0 and Q1 and Q such that Q0 intersect R equals Q1 intersect R, then Q0 and Q1 are not comparable. So another way of sort of visualizing an extension that's inc is you cannot have 2 primes that are comparable that contract to the same prime ideal below. So if you have little guy inside big guy, they can't contract, they can't both intersect at the same time. So these are the kind of some big important properties that ring extensions may have. Lying over. Anybody give an example of an extension that is lying over? Any ideas? You've got to give me 2 rings, right? Well, that's a yes. Your example's too good because yes, and in fact, his example's a ring algebra, and so I'll record that. You really got out the nuclear weapon on that one, didn't you? Right? Because actually, as it turns out, any prime is actually lined up by infinitely many primes. It's big. Let me give one more. It will be easier for me to show you. Right. Let's look at Z level and the CX level. I want to give you 2 kinds of primes. 0 is laying over by X, and I just did that to be interesting because 0 is also laying over by 0. All right. Notice that this is right. So 0 and X go here. And how about P? That's a more general prime. I can actually see 2 here. This extension, so I'm basically kind of giving you a formula for everything that's laying over. There you go. But this extension is not inc, right? Because in both these cases, here are two different ideals that are comparable, two different prime ideals that both lie at the same prime, right? So this is lying over, it's not inc. Is it going up? Can anybody fill in the three white ones? You're not gonna be able to do the yellow one. So, yeah, actually, it's probably is coming out. So, what kind of change of primes do you have down here? If you look at ZX. So for ZX, that's really the only thing that's relevant, right? Because you don't want to double up on these because then you clearly can do it, right? What are your choices here? Well, if if you have this, then you can go up P of the ZX, right? This is, remember, P is prime here and it's still prime here, so no problem. So you can do it this way. What's your only other option here? What else lies? Well, actually, what lies over zero? X. If you look at X here, you can go up EX. What else though? So does that kind of settle it? Can you always go up? Have I covered all my bases? Sometimes this can be subtle. Let's look at this example here. Let me give you something specific. Here are two primes here. Given any prime that lies over, can you always go up? I don't think so. Let me first make a couple of observations. 2x plus 1 is actually a prime element in here because this is a unique factorization domain and this is an irreducible polynomial. Okay, so this is a prime ideal, and of course 2x plus 1 times another polynomial has to have degree 1 or greater, right? Unless you multiply it by 0, right? So the intersection down here is 0. Right? Can you go up? So now you've got to find a prime ideal Q that intersects down here, right? So to go up to Q, you need that Q is in Q, correct? And also, 2x plus 1 must be in Q. Therefore, 1 is in Q. So it looks like going up doesn't work. Okay, lying over. Whenever I think about lying over, I think, well, it seems to always happen. Can anybody give me an extension where you don't have lying over? And when you think of the example, you will chortle to yourself. How about this? Give me a prime, stop laying over, any of them except 0. No prime. Like Q intersects. Because in fact, the only prime in Q is 0, right? So this one's not lying over. However, we're going to see a big class of things. So I hope this example illustrates that, this can't happen. I mean, the polynomial extension Z inside ZX, that's about as good as you might expect to encounter, but it still doesn't have this property that you can build up stacks of primes this way. So let me give you some theorems, a couple of similar theorems. One about going up and one about inc that sort of connect into multiplicatively closed sets, which is kind of cool. Theorem. And actually, both of these next couple of theorems, I wrote a paper many years ago where I use this rather extensively. Number one, what did I say for that one? R inside of here rings. Following conditions are equivalent. Number one, R inside T is going up. So the extension has this going up property. And 2, if P is a prime ideal of R, and S is its complement. And S is its complement, and Q is a prime ideal of T that is maximal with respect to the exclusion of S, then its intersection downstairs is precisely. And Q in T is a prime maximal with respect to the exclusion of S. And just to be clear, I mean by that, of course, Q intersect S and then Q intersect S, not S, Q intersect R. Okay, so let me point. This kind of theorem always bothers me a little bit because I want to make sure that I'm on the right page here. The first thing is, I mean, the obvious question that springs to mind is, I state, and suppose Q is a prime maximal with respect to the exclusion of S. Does this exist? You bet your bottom dollar, because S is a multiplicatively closed set of R, and R is contained in T. So S is a multiplicatively closed set of T as well. There certainly is an ideal in T that misses S, namely the 0 ideal. All right, and I can expand that ideal to an ideal that's maximal with respect to the exclusion of S. So yes, indeed, always this happens. There is such an animal. And what this says is any one of these that you happen to find, they all intersect down to P, right? let's point out the interesting part of this. So, proof, I'm not going to formally start yet. Let me just kind of make these statements. Note, S, a multiplicative subset closed. And in fact, in this case, it's saturated in R. So S is a multiplicative closed subset of R and hence T. So there exists a Q in T maximal with respect to the exclusion of X, exclusion of S, and of course Q prime. It's amazing how many that old hat just keeps coming back. Also, let me point out what can you say? So that means Q misses everything that's not in P. So that means this is always the case. Right. Because, right, Q misses this multiplicative set S. So it misses everything that's not in P. So when you intersect Q down to R, everything in Q intersect R is contained in P, right? So the interesting thing we're going to have to show about is the reverse containment, that everything P, everything that's in P is actually in Q. So let's get more formal proof there. Okay, so suppose we've got this mouthful here, and we need to show that it's going up. So suppose we have a chain of two primes of R and Q0 in T is a prime such that Q0 intersect R is equal to Q0. So here's the situation we've got. And what we got to do is we've got to build this Q1 now. That's the burden, and we get to use property 2 to help us out. So notice that Q naught intersect S is empty, where S is the complement of P1 and R. So yes. Let's let S be R minus the bigger prime. And notice that Q naught intersect S must be empty. Right, because if you Q naught intersects down inside of P naught, right? And so in particular, everything that's outside of P1, maybe a diagram might help. So here we have P naught. Here we have the perhaps bigger P1. Now Q naught contracts to P naught, right? And so that means that everything in Q naught is here, S is the complement out here. There's no way that anything in Q naught, which contracts down here, picks up stuff outside, so that's okay, right? So let's expand P naught to Q, Q naught to Q1, the maximum, with respect to the exclusion of S. Let's expand Q naught, Q1, A prime, and T maximal with respect to exclusion. S. So just grow that to a prime that's maximal with respect to the exclusion of S. And notice that if you have Q1 intersect R, so you've got filling out. How about the other direction? So now we've got to kind of troll through the other direction. So in this case, let's let Q be maximal with respect to the exclusion of S, which is the complement of P and R. And so what we have to do is we need to show that, of course, that this the Q must intersect back down. When you intersect Q with R, it must intersect back to P. So what do we have? We've got going up. So we must show the Q intersect R. So that's our big goal here. So we know that Q intersect R is some prime. And in fact, as we pointed out before, it must be contained in P. And going up allows us to expand this to a prime Q1 lying over P. Going up, expand Q1, A prime lying over. So what we have now is Q and Q1 both lie over P. But we know that we know, but by assumption, Q is an ideal of T that is maximal with respect to exclusion of S. By maximality of Q equals Q1. And we have what we want, so it must lie over. So since Q1 lies with P and Q equals Q1, then we've got what we needed there. Okay. Okay, any questions on that? Okay, here's an interesting, maybe it's not completely clear from the definition, but got it now. Corollary. Any extension, if you've got going up, then you've got lying over, right? Let me search this. If R inside P is going up, then I'm going to use this condition 2 from the previous theorem. If P is a prime ideal of R, and S equals R minus P, and Q is maximal in T such that Q intersect S is empty, then Q intersect R. And there's your line over. An arbitrary prime is line over from something else. Okay. Any questions on that? By the way, I like my other example because if we saw earlier, we had the Z inside ZX was lying over. It wasn't going up. So that quick example shows that in general you can't expect the converse. If you have going up, you have lying over, but lying over is weaker. You don't expect it to be equivalence. Okay. Any questions on that? All right, so here's another one. This is like similar to the last one, only it's with ink. Let R inside TB rings. Number 1, ink holes. And 2, if P and R is a prime, and Q and P is prime, such that Q intersect R is P, then Q is maximal with respect to the exclusion of S. So if P is a prime ideal and Q and T contracts to P, then Q is maximal with respect to the exclusion complement of the original prime P in R. Let's go through this. Okay, see if you guys can help me out on this. Okay, so we have 8 holes. What does that mean? That means if you have 2 primes that contract to the same prime below, then they can't be comparable. So how are we going to, given ink, how are we going to show this? Well, suppose Q and T is prime, and Q intersect R is equal to P. We need to finish the statement. We need to show that Q is somehow maximal with respect to the exclusion of S. Suppose you have another prime. Let's do one. Well, let me point out before I get carried away. Note that Q intersect S is the empty set. Right? Because the fact that Q intersects down to P means that when you intersect Q down to R, it can't pick up anything outside of P. Right? Which means that it can't have any overlap with S. Remember, S is a multiple close subset of R, right? So everybody cool with this? So that observation is going to be important. What we have to do is show that Q is maximal with respect to the exclusion of S. So suppose there exists another prime, Q1, such that and Q1 excludes S. So again, Q1 intersect S is empty set. Well, this means, again, Q1 intersect R is actually contained in P, right? Because if it excludes S, when the intersection of R is contained in P, and since Q is contained in Q1, this means Q1 intersect R is equal to P as well. So now you have two primes, Q and Q1, both intersecting with P. So if I ink Q equals Q1, because you can't have two comparable primes intersecting the same thing. Therefore, Q is maximal with respect to exclusion of S. But okay. Okay, so how about the other direction? For the other direction, for 2 implies 1, all right, so let's suppose we have the statement that if you have any prime contracting to a prime below, the Q is maximal with respect to the exclusion of that. Well, let Q0 and Q1 and R be primes. Yeah, we're trying to show ink holes such that Q0 intersect R. Note that right, because since they both here or S, because of the fact that they both intersect down into P, that means they both have to miss the complement of P. Right? And so since Q0 respectively Q1 contracts P. Q0, respectively, Q1 is maximal with respect to missing S. So either Q0 equals Q1 or they are not comparable by maximality. Okay, any questions on that? Actually, these other characterizations of ink or the other characterization of ink going up are very useful. And in fact, here, let me give you kind of, this is kind of the big thing that we're going for here. This is, I love this theorem. Let R inside T be an extension of rings. With T interval over R. Then T, well, then R inside T, I can say it that way, is going up and in. This is a super, super cool result because what it means is for interval extensions, right? And of course, a lot of the stuff that I'm interested in number theory, right? That these algebraic number rings, they're integral extensions. So whenever, so in a certain sense, with respect to these kind of pairings of ideals, if you have, for example, R is the integers and T is a ring of algebraic integers, then this extension, because it's interval, is both going up and in. And this is actually very, very important because in a certain sense, there are some properties of the integers that are mimicked very much by the more general structures. Let me, this proof is rather lengthy here. Let me give you a corollary. Let me give you a couple of corollaries actually. Okay, so that one's a little bit silly because we already know that anything's going up this line over. So we kind of get that. Here's another index. And we're going to work up to this. So I'm going to prove the theorem 515 next time we'll come work up to this. Dimensions on the same. This is actually, and that's the important about going up and ink. Right. So let me give you kind of a fun clue to think about as you cogitate this for the next time. But the reason this holds right here is one of the properties going up or ink gives you this inequality. And the other one gives you the other inequality. So see if you can figure out which is which, right? So for example, whenever you have a going up extension, you have one inequality on fold dimension, and for ink, you have the opposite. Okay, any questions? Yes, sir.
So in a general setting of three extensions, is there a way to immediately compare the size of, like, to compare the dimensions? It's like,
I mean, if you let me be completely free and loose, then I can make it awful, right? I can take a field inside of a polynomial ring over that field and uncountably many variables. I can just go table, you know, so. Okay. All right, well, you all have a good one, and we will see you next time.